Everyone again, this is 5.2 logarithmic functions and their graphs. And first I want to recall exponential functions. And I'm going to write y equals instead of f of x equals. So y equals b to the x, where remember the base is positive and not equal to 1. And I'm going to first describe the logarithm as being essentially the inverse of the exponential. So an exponential form is a form of, well, y equals something to the x, b to the x, where logarithmic form, on the other hand, is log base b of y is equal to x. So these are the same components here. So b is the same, and y is the same, and x is the same. So the way I often like to phrase this is the way you phrase this is you say log base b. So this is the base just like this is the base. So they have the same base. That's something to keep in mind. In fact, I'll write that here. They have the same base. It's easy to remember if you remember writing it like that and saying log base b. Don't say log sub b or log b. You say log base b. Okay? And it's of y. Y is what the exponential is equal to. That normally doesn't have a name. Sometimes some people call it the resultant. I'm not going to call it anything actually. Just call it the other number. But the one I do want to focus on is x. So what is x here? It's not obvious. It's what log is equal to. But here, x actually has a name. X is the exponent, or the power. So what we get from this is that logs solve for the exponent. So you can write that here as a nice note. Logs solve for exponents. And I think that's very, very, very important and key. And that'll help you transition, or I guess translate between logarithmic form and exponential form. The first thing I want to try to do here is get us used to translating between these two forms. So here I say convert between the two forms. So here this is in logarithmic form, of course, and this will be in exponential form. So let's see if we can get a handle on converting. So I want to first find the base. What is the base? Well, read this out loud. It's log base 4 of 16 equals 2. So the base is 4. Okay, so it's going to be 4 to the something equals something else. So now what's the power? Remember, logs solve for the exponents or the powers. So that means since this log is equal to 2, then the power must be 2. What does that mean about the other number? It must be the other one we haven't used yet, which is 16. And this is certainly true. 4 to the 2 is equal to 16. So that's what log base 4 of 16 equals 2 says. It says that the inside is the base to that power. So log base 4 of 16 asks the question, what power of the base 4 will give you 16? And the answer is 2, because 4 to the 2 is 16. Good. So now how about here? Well, here the base is also 4, so this is going to be log base 4 of, I should box this answer by the way, just like I'm going to box this one shortly, of what equals what? Well, again, what do logs solve for? So we know the base is the same. We already got that down, it seems. But logs solve for the exponent. And the exponent here is negative 3. So 4 to the negative 3 is equal to the inside, which is the other number we haven't used, and that's 1 over 16. So log base 4 of 1 over 16 is equal to negative 3. And there we go. Now we're going to write the logarithmic function a little more formally and look at the graph. All right, so here I say a logarithmic function is one of the form f of x equals log base b of x, where b is, of course, positive and not equal to 1, just like we saw for exponentials. And for the graph, when b is positive, or b is bigger than 1, I should say, the function will look something like this. Has an x-intercept at 1, and where it is less than 1, but of course bigger than 0, the graph will look something like this, and have an x-intercept at 1. Now it looks kind of like there's a horizontal asymptote, but there's not. It actually continues to increase. Similarly here, it continues to decrease. So of course, yes, just like we saw for exponentials, there's an increase inversion and a decrease inversion. And also, we have some things in common. Here's what we have in common with these graphs. So notice there's a vertical asymptote at the y-axis, much like for exponentials. If you look back at that video, we saw a horizontal asymptote at the x-axis. Here it's a vertical at the y-axis. So very, very similar, just kind of the opposite for all of these, in fact. So there's an x-intercept at 1, 0 instead of a y-intercept at 0, 1. And the domain here is 0 to infinity. The range is negative infinity to infinity. If you look at 5.1 for the exponential function, the domain and range were flipped. And just like the exponential function, logarithmic functions are also 1 to 1. Okay, now why is there so much similar and why are they opposite? Well, it's obviously because what I mentioned earlier, they are inverses of the exponential function. So if you were to, let me see if I can show you here in, I guess that's fine, in red. If I draw a line y equals x, and I reflect this curve about this red line, what I end up getting is this graph. And this graph is y equals b to the x. Where this curve, of course, is y is equal to log base b of x. And if you recall from inverse functions, that we saw a while ago actually, that is true. If you have inverses, then their graphs are just reflected about the line y equals x. And I could show it here also. It just looks a little funny here. But if you reflect about the line y equals x, so grab a point here and reflect it over, grab a point here, reflect it over, and you keep doing that, you're going to end up getting this curve here. I didn't do it too much justice, but it actually does reflect to this exactly. And these red curves that I'm drawing here, not the lines, but the curves, are exactly what we saw for the exponential functions. So all I really want to say here, basically from the graph, is that we have the inverse of the exponential. The biggest note, I think, is the domain is 0 to infinity, meaning you can't plug in a negative nor 0 into log. So this x cannot be equal to 0 and it cannot be negative. So it cannot be equal to 0 or less than 0. In fact, according to this domain here, it has to be in between 0 and infinity, not equal to 0, so only positive numbers, not even 0. So that's something important to note. Also, the range can be, though. The range can be 0, the range can be negative, so the output could be negative number, 0, or positive as well. And yes, it is 1 to 1. We'll see that in use right now. In fact, a lot of this phenomenon here will be explained. Right now, we're going to talk about some really, really interesting properties. And basically, we're going to relate it back to the exponential. So to be quite honest, the graph isn't so much important as the previous thing we spoke about, which is comparing those forms and converting between. Because we're going to be very often comparing a logarithmic form to exponential form so that we can use exponential properties to discover new what are called logarithmic properties. So let's take a look, see how that goes. Right, so here now let's talk about some logarithmic properties. Here I say basic, of course, because 5.3, if you take a look, the title of that is properties of logarithms. So we'll see some more properties that are not as basic as these ones. But yeah, so I'm going to fill in the blanks here and tell you what the properties are. I'm also going to, below here, try to explain each of them one at a time. So let's see. And by the way, the explanation will have to do with what I was saying earlier as far as converting between those two forms. So let's have a look now. So log base b of 1, no matter what the base is, this has to be equal to 0. And this, of course, is because if you convert this into, I guess maybe I'll do it here, but if you convert this into logarithmic form, or into exponential form from a logarithmic form rather, you get that the base b to this power would be equal to 1. And of course, this only happens when either b is 1 or the power is 0. But since the base is never 1 for these cases, this must be 0. So then translating it back to logarithm, we get this, that the power must be 0. So there you go. Here, if you were to convert this into exponential, you would say the base to what power, which is this answer here, is equal to the inside, which is b. So of course the answer here is 1, b to the 1 is equal to b. So translating back, this must be 1 itself. Perfect. Now 3. 3 is a little hard to explain, it's not too bad, but let's take a look down below here. So again, converting this to exponential, the base is b, so b to what power is equal to the inside, aha. If we apply the one-to-one property of exponentials, since the bases are the same, the exponents must be the same. So this question mark value must be equal to x itself, in order for the exponents to be the same. So this actually must be x. Great. Now what about this? Well, let's see. Well, here this is actually, believe it or not, this is an exponential form, so we have to convert it into logarithmic form. So we'll say that log base, the base is b, of the inside is, well, we don't know what the inside is actually, equals the power, because logs solve for powers. So the power in this case here is log base b itself, log base b of x. And like we saw in the previous screen when we discussed graphs, we saw that log base b of x was a one-to-one function, meaning if log base b of something is equal to log base b of something else, then the exponents, well, not the exponents, but the insides must be the same. I almost said exponents from the one-to-one property of exponentials, but it translates over quite the same. So if log base b of something is equal to log base b of x, then that something must be x itself. So this is actually equal to x. And very often, these two properties in 3 here is often known as cancellation. So log base b of b cancels and you just get x. B to the log base b of x cancels and you just get x. Good. And now finally 4. 4 literally is just the explanation of the one-to-one property that we just used actually. If log base b of x1 is equal to log base b of x2, then x1 must be equal to x2. There we go. And I was going to do some examples of these, but to be quite honest, they're a little too simple. Instead of doing that, here's what I'm going to do. I'm going to introduce some special types of logarithmic functions with special bases, and from there we'll do some examples involving these. Right, so here are the special logarithms. There are 3. Actually, there's usually 2 that are mentioned, but I want to show you this third one, binary. Computer scientists in particular like binary log. It's used a lot because, of course, a binary representation of a number that's often used a lot in computer science if you think of like ones and zeros and so on. And the common or decimal log is just log of x. Notice there's no base in the name. Natural log is ln of x for, well, log natural, which is kind of the Latin phrasing of natural log. Otherwise, we would use nl, but we just use ln because of tradition, basically. And lg, which is, of course, kind of just the 2 letters of log, the first and the last. And here's what they mean. So log of x is log base 10. So if you ever see a log without a base, we assume the base is 10. That's a common log. Okay, that's why I say decimal. Decimal means 10. Good. What about ln? Well, what do we know about natural? Can we think of any number that we've seen recently that we called a natural number? There's the natural exponential e. So this is actually log base e. So if you ever see ln of x, that just means, well, log base e of x. And then lg of x is log base 2, but we're not really going to see it. I just wanted to show that there are other special logarithms besides just the common and natural one. Anyways, let's move on to do some of these examples. Now these examples, believe it or not, are just examples of the previous properties we just saw, but only with these logarithms, except of course the binary one. Now, first off, this is log of 1. Now remember, this is log base 10 of 1, and log base, any base of 1 is always 0, because any base to the 0 is equal to 1. So if you want, you could say because, well, 10 to the 0 is equal to 1. So if you were to write this in exponential form, the base is 10, the power is 0, and it's equal to 1, so it must be equal to 0. All right? Here, well, this is just 17, because of the property we saw where the bases cancel. So here, this is because ln means log base e, so this is log base e of 17. And as I explained previously, if you ever have this situation where you have log base something of the base to some other power, so log base, whatever the base is, of that same base to a power, the bases cancel, well, the log cancels as well, and you just get 17. And this is actually very similar. This is the opposite version of that property. here, since this is technically log base 10, these cancel and we just get 32. And I should box these answers. And finally, this is log base E, because ln means log base E. So let me say that this is really log base E of E. And we saw that, well, there's two ways of explaining it now, because we have basically number 2, but now where the power here is 1. So these would cancel and we just get 1. And the other way of explaining it was the one-to-one property. And we actually saw this in the previous when I mentioned the properties previously. But in any event, here are some examples of those properties by using these special names for logarithms. Now finally I want to do some more examples of just solving involving logarithms. Alright, so finally now let's see this example where I want to solve for x in each of these 5 parts. And notice they're all logarithmic form, so I'm going to convert them into exponential form and let's see if we can get something going. So this in exponential form says 3 to the, because that's a base 3, to the power is 2 because log solve for powers, is equal to the inside x. So this of course means x is equal to 9, and there it is. So in fact we can say log base 3 of 9 is 2. So there we go. There's a nice way of using logarithms and converting between logarithmic and exponential form to actually evaluating certain logarithms. So a nice consequence of this equation here, or I guess of this example, is that log base 3 of 9 is equal to 2. Okay? What else? Oh, here, so this is a little different. X is in a different location, but we're going to convert the same way. The base is 5, the power is x. So 5 to the x is equal to 125. And we saw these types of problems in 5.1. We write both of them in the same base. And in this case, if you look at the base 5, powers of 5 are, well, if you think 5 to the 1, 5 to the 2, 5 to the 3, 5 to the 1, of course, is 5. 5 squared is 25, and 5 to the 3 is 5 times 25, which is 125. So 5 to the x is equal to 5 to the 3. So by the one-to-one property of exponents, that means x must be equal to 3. Great. Let's see, what about this one? Here this says log base x of 8 is equal to 3. So converting this into exponential form like these were, so let me write that arrow here. So labeling the arrow as exp for exponential, converting this to exponential form, the base x to the power 3 is equal to 8. If we cube root both sides of this equation, here we get cancellation of the powers and we just get x is equal to the cube root of 8, which is 2. So x is equal to 2. Nice. This is going to be a little difficult. So we know this is log base e. So keep that in mind. Converting this to exponential now shouldn't be too bad. We get that the base e to the power of x, because logs solve for powers, must be equal to the inside 1 over the square root of e. Now, I'm going to try to write this as a power of e, and here's what I'm going to do. I'm going to say that, well, remember I mentioned this before, the square root is the same as 1/2 power. So this is e to the 1/2 in the denominator. In other words, it's the reciprocal of e to the 1/2. In other words, we can write this as e to the negative 1/2, because that's after all what negative powers mean. They mean reciprocals. Now, if we just relate these two, because this is of course all equality, so basically ignoring the middle two, then using the one-to-one property of exponents, what can we say? Finally, we can say that x is equal to negative 1/2. Perfect. And remember, I said the inside of logs cannot be negative. Their outputs can certainly be negative. So this works, actually. Great. Now, this is log of 1 million equals x. What does log mean? Log means log base 10. So now writing this in exponential form is the base 10 to the power of x is equal to 1 million. 1 million is 10 to the what? Well, if you didn't know this already, 1 with a bunch of zeros after the 1 is just 10 to that amount of zeros. So this is 10 to the 6 because there are 6 zeros after this 1. So you can do that with any number that looks like that. 1 and then a bunch of zeros, it's 10 to the amount of zeros. So now again, ignoring the middleman here and just comparing these two, 10 to the x is equal to 10 to the 6, and using the one-to-one property of exponents, we get that x must be equal to 6. Nice. Very good. So that concludes 5.2, and now in the next section, 5.3, we're going to see some more properties of logarithms. It's going to be really, really, really interesting stuff. And then finally, we're going to use all of that information in 5.4 to solve even crazier types of equations involving logarithms and even exponentials that we couldn't solve before using 5.1 methods. It's going to be a lot of fun. See you in the next videos. Thanks for watching.